final video report for Texas Instrument Innovation Challenge India Design Contest 2015. Team number 1605, performance enhanced 3-phase PWM inverter based induction motor drive. Team members DB Ratnayaka, SMHK Samarasinghe, CI Matagedara, PB HPB Ganegoda. Faculty mentor Dr. SG Aberatna. Motors are widely used in industrial applications, and out of them, 90% of them are induction motors. Hence, the performance of the induction motor directly affects the industry. Let's take a look at the typical arrangement of an induction motor drive. Here, we have 3-phase sinusoidal waveforms, and those are fed to the AC to DC rectifier. Here we are considering a voltage source inverter. Because of that, at the output we have the DC link in order to maintain a constant voltage. So that constant voltage is fed to a DC to AC inverter, and the switching mechanism for the inverter is chosen as pulse width modulation. At the output of the inverter we have an induction motor connected. So by changing the amplitude and the frequency of the reference wave, we can easily change the output voltage and the frequency, and by that we can control the speed of the induction motor easily using an inverter. In order to improve the performance of the induction motor drive, we must improve the performance of the inverter. Performance of the inverter is being compromised by many factors. Dead time, harmonics are a couple of them. Typical arrangement of an inverter is shown in the figure. Only one leg of the inverter is shown here. There are 3 legs in a typical 3-phase inverter. There are 2 switching devices in a leg, and each has a freewheeling diode. And the switching pulses are generated by a PWM generator. The DC link is shown as a constant voltage source. Performance of the inverter is being degraded due to many factors, and the dead time is one of them. Since the practically available switching devices are non-ideal, there's a finite turn on and turn off times. Hence, in order to avoid a shoot through in the DC link, the turning on device is being delayed by a finite time amount. This delay is known as the dead time. This very delay causes serious output distortions and results in harmonics. As shown in the figure, because of this delay, there is a finite time where both of the switching devices are at off state. Here. At this time, the voltage is solely dependent on the current direction. If the current is into the motor, the negative rail will be short circuited and the output voltage will be negative. Likewise, if the current is into the motor, the positive rail will be short circuited and the output voltage will be positive. So, depending on the current direction, there will be either a loss or a gain in voltage seconds. Even though this amount appears to be small, when it is accumulated throughout the operating cycle, the distortion is significant. Hence, dead time must be compensated accurately. There are many already available methods to compensate the dead time, but most of them compensate only the magnitude. Some compensate phase as well, but they require a lot of processing power and memory because they use complex software algorithms. Existing methods can be divided into 2 main categories. First one, average-based methods. In average-based methods, the reference wave is modified by adding or subtracting the error voltage that has been averaged over a half of operating cycle. And the other method is pulse based method, in which the correction will be done by pulse. The rising edge or the falling edge will be delayed or advanced by a finite dead time amount depending on the current direction. In this project, we have proposed a method to correct the dead time more accurately. The proposed method corrects the magnitude as well as the phase. As shown in the figure, the proposed method uses the edge delaying method because it requires less processing power, less memory, and the resource allocation will be far better than the other methods. The left side figure is for positive current direction and the right side figure is for negative current direction. So depending on the current direction, either the rising edge or the falling edge will be delayed. But as you can see in the figures, due to this delaying, the output waveform will be delayed by a finite time amount. In order to avoid this delay, a small modification is done in the PWM generation. The proposed induction motor drive comprises of three parts: the dead time delay circuit, edge delaying circuit, and also the PWM generation block. In dead time delay block, a small dead time is added in order to avoid a shoot through in the DC link. Edge delaying circuit is to correct the magnitude distortion caused by the dead time. To correct the phase delay, a simple modification is done to the reference waveform in the PWM generation block. This is the practical implementation of the project, and we have used high voltage motor control and power factor correction developers kit, and we have interfaced it with a 3-phase squirrel cage induction motor. It is a 0.33 horsepower induction motor, and you can see the motor